Good morning, students. So, welcome to GATE class on communication system. Okay, so a few students need to join, but I will start the class because as per schedule, we need to start. Okay, so 9 to 10 is a session. Okay, so today's GATE class is all about communication systems. Okay, so some students already are familiar with communication because some final students are there, and third years they have started preparing the finished their analog communication. Right now, they're studying digital communication in their sixth semester. Their second year, then it's new concept for you. Okay, so basically communication system is nothing but how we are communicating. Okay, so communication means confirm, it requires transmitter, receiver, in between certain blocks. Okay, so the information which we are giving is always analog signal. Okay, so we are giving an analog signal to a system. The output which we are expecting is an analog signal. Okay, so if we are processing this analog signal as it is, then we have to, it is called as analog communication. If we are converting this analog signal to digital communication, then if you are processing that one, that is called digital communication. Okay, so both the things, both things we have. Okay, so we have analog as well as digital also. Okay, the thing is, we have certain rules. So when you are transmitting certain information, there should not be any error when we are recurring. Okay, that's why we need to follow certain rules. The first thing is we are going for sampling. Okay, sampling is nothing but so whenever we are sending a message signal, that should be recorded without any loss. Okay, so the minimum condition for that is Fs is equal to 2Fm. That is message signal twice of the message signal. Fs is equal to 2Fm is the formula. Then we can able to recover signal without any loss. The Fs is the sampling frequency and Fm is the message signal frequency. So always my message signal frequency should be twice as it of sampling frequency. If it's less than that, what happens? There is overlapping of signals will happen. So confirm we can't able to recover the information which we have said. So that's a main problem when we not following the Nyquist state. Okay, Nyquist state is nothing but the formula for Nyquist state is Fs is equal to 2Fm. So always when I want to recover signal without any loss, the minimum condition is required is Fs is equal to 2Fm. But Fs is the sampling frequency, Fm is the message signal frequency the message which we are sending. Okay, so this is a minimum criteria to get back signal without any loss. Okay, it can be Fs should be greater than is equal to Fm. This is the actual condition. But if is equal to means exact is equal to means is called as Nyquist state. Okay, so this is a base for any system. Okay, even if you are going for digital communication, if you are going for analog communication, it's a base. First system we are going for sampling. Okay, then we will go for quantization. There is nothing. Sampling is nothing but converting any given continuous time signal and continuous sample signal into continuous in amplitude and discrete in time signal. So that is nothing but this concept is called as sampling. Okay, because confirm the given signal will be analog type. This is nothing but the given information source. Everything is analog signal. Now sampling means in time. So in time, I'm going to again. So for each time period, I'm going to sample. This is called as I'm breaking the continuous in time signal into discrete in time. So this process is called sampling. The next process, as I said, is quantization. So quantization is nothing but this amplitude. This entire amplitude is nothing but continuous. Now I need to break this continuous amplitude to discrete one. That process can be done with the help of quantization. Okay. So then what I need to do after doing this two process, I need to go for making it a pure words, pure digits or pure bits. So that is called as conversion or to digital conversion, which will give the desired outcome of bits. Okay, so the combination of sampling, quantization, as well as the encoding, this three is called as analog to digital communication. Okay, so when you are going for analog communication, we no need this three process. Directly we can able to process it. If we are going for digital communication, we need to do these three process to get the desired outcome. Okay, so now we will see some problems based on these things. Okay. So the first problem is sampling. We will go with sampling. A band limited signal is sampled at the Nyquist state. So Nyquist, as I said, Nyquist state is nothing but Fs is equal to 2Fm. So this is the minimum condition. Okay. So the main thing is here, the signal can be recovered by the passing samples. So where I need to pass this, in which filter I need to pass this to get the desired outcome. Okay, that's the question which they asked. The answer is, as I said, a continuous time sample as Nyquist trace is given as Fs is equal to 2Fm. So now I need to recover this without any loss. Okay, so for the purpose, I need to use a band limited low pass filter because I have some cutoff frequency. More than this frequency, the components can be eliminated, only the corresponding components will be recovered. Okay, so I need to pass the desired results to a low pass filter with that limited bandwidth. Then only I can able to get the desired outcome. Okay, that's why these four options. My answer is I need to use a low pass filter with appropriate bandwidth. Okay, then only I can able to recover the correct information without any loss. Okay, so this is the actual definition for sampling. Okay, sampling definition. This is a definition for sampling. Okay, any bandwidth signal with the desired frequency range and with the desired bandwidth, I can able to recover the signal without any loss by using a low pass filter. Okay, so this is the answer for the first question. This question is asked in 2001 gate. Okay, this question is for 1 month. Okay, so this is the answer. So second question, a deterministic signal has the power spectrum given the figure. The minimum sampling rate needed to completely represent the signal. Okay, so they ask for the sampling rate Fs. Okay, the minimum sampling rate. Okay, so if we consider this diagram, in this one, it consists of some information which I'm going to share through the receiver. Okay, so here we go to this one. Here some information is available. Here some information is available. Here some information available. Okay, among these three, the maximum information is available at this end only. This end, because this is the main lobe. So main lobe consists of maximum information compared to this minor lobes. So minor lobe, minimal information is there. Even there's any noise available, if this corrupts means it's no issue because we have maximum information available at the main lobe only. Okay, so this main lobe represents the main signal. Okay, so by considering this one, we need to proceed with the formula. Okay, so here, as I said, the main lobe consists of the main information. Okay, it's the maximum frequency for this one is 1 kilohertz. Okay, the main lobe in frequency is 1 kilohertz. So now based on this, so as I said, 90% of information, transmit information is available in the main lobe. Remaining 10% is available in the minor lobe. Okay, if we explore this minor lobe, no issues at all. We'll consider main lobe and we will try to find the signaling rate. Okay, so the minimum sampling rate is given as I already said that the equation is given as 2fm. So Fs is greater than equal to 2fm is the actual formula, but when Fs is equal to fm, that is called as sampling rate. Okay, so they ask for minimum sampling rate. It is given nothing but Fs is equal to fm. Okay, so we have taken the frequency rate is 1 kilohertz. Fm is 1 kilohertz. So the sampling rate is nothing but 2 into fm. So the required answer is 2 kilohertz. Okay, so in this available options, the answer is we can find the 2 kilohertz at B. Okay, so for the given problem, the minimum sampling rate is required is 2 kilohertz. Okay, because Fs is equal to 2 fm. So fm, the message frequency is maximum frequency is taken as 1 kilohertz. Taken as 1 kilohertz. That's why fm is substitute 1 here in fm. We'll get 2 fm as the answer. So next problem. So a signal has frequency components from 300 hertz to 1.8 kilohertz. The minimum possible rate at which the signal has to be sampled. So they ask for again the minimal possible rate, where we can able to sample this given frequencies. Okay, so here they are given two components. One is higher frequency component and next is the lower frequency component. So we need to first find the bandwidth. Okay, so here FH is 1800 hertz and FL is 3300 hertz. Okay, from this bandwidth formula is nothing but FH minus FL, high frequency components minus low frequency components. So the outcome is 1800 minus 300, which is nothing but 1500 hertz. Okay, then the M is a modulation index formula, which is given as M is equal to FH by bandwidth, because FSM, they ask for minimum sampling rate, possible rate, Fs minimum is given as 2FH by M. Okay, so you need to find M value. So M value is given as, okay, FH by bandwidth, FH is 1800 and bandwidth BW is 1500. So if we divide these two, we got 1.2. But now we need to round it up to the nearest possible integer. Okay, so there's nothing but we'll get integer as 1. Okay, So now substitute this value in the formula. Fs minimum is equal to 2Fs into M, where Fh is equal to 1800. So 1000 into 2 is 3600. Okay, by 1. So the answer is 3600 samples per second. Okay, so there is a fill in the blanks option. Sometimes at times they will give fill in the blanks also. So we need to solve accordingly. We need to give the answer in the blanks. Okay, so the desired answer is 3600 samples per second. Okay, so sampling can be done. We can call it a normal sampling, then flat top sampling. Normal sampling means directly sampling this given signal. Flat top sampling is nothing but we are going to consider a rectangle where sampling will be done at the flat top. So everything at the edges, flatly we are going to do it. Okay. So here the next question is for flat top sampling of low pass signals. Okay, when we go for flat top sampling compared to a normal, what will happen? What is the impact on this flat top sampling? Okay, so flat top sampling, we have certain disadvantages also that is covered here. Okay, so go to the solution. So flat top of low pass signal has a spectrum of sinc function. So when we try to send this sine function to a transmitter, the outcome of any the outcome of the receiver is nothing but a sinc function. Sinc function is nothing but this is sinc function. Okay, so as I said previously, we have seen a diagram, main lobe and two major lobe and main lobe and two minor lobes. So that is nothing but sinc function. So when we try to transmit any sine wave function, okay, when we take a sine wave of any function, the desired outcome, okay, the desired outcome at the receiving end is nothing but a sinc function only. Okay, so this is applicable for flat top sampling also. Even if it's a normal sampling or flat top sampling, the desired outcome of the sampling is nothing but at the receiving end is nothing but a sinc function. Okay, so now as we are using a flat top sampling, what will happen means the peak amplitude. Okay, the amplitude is reduced. For the highest components of amplitude is reduced because it's a flat top sampling. Even we have the sine function, if you make it as flat, I'm going to miss this component. Okay, I am going to miss this component. If I use flat top sampling for a sine wave, because flat is going to consider. Okay, it's going to miss certain information. So that's why this effect is called as aperture effect. Okay, so highest frequency components is reduced. The amplitude of highest frequency components is reduced. That effect is called as aperture effects. Okay, so what will happen? So flat top sampling gives rise to aperture effect. So we have there are given 4 options. Oversampling leads to aliasing, interaction, delay, distortion. Nothing is possible with the help of flat top sampling. The highest amplitude component is reduced. Okay, so those effect is called as aperture. That's why flat top sampling of low pass signal gives rise to aperture effect. So how can we reduce this? By increasing sampling frequency, we can able to reduce the aperture effect. Okay, as the width is the aperture width is keep on increasing, my aperture effect is keep on increasing. Okay, so as width is increases, my aperture effect is increasing. That is, the highest amplitude is keep on reducing. That means the useful information is minimized. Okay, so we need to make sure that the width of aperture window should be very minimal. Then only without any loss, I can able to recover signal without any loss. Okay, so that is the option. So the flat top sampling gives rise to aperture effect. Okay, so next question, fifth question. Increased pulse width in the flat top sampling leads to. Okay, so as I already said that flat top sampling spectrum of sinc function. Confirm will get this sinc function. So as I already said, amplitude is keep on reducing. This effect is called aperture effect. Okay, so as I said, if you go to this one, as sampling aperture increases, the increase of pulse width, there will be more loss in high frequency components. So same thing. So previously here, as width increases, loss increases. Okay, so both are similar. So this question is asked 1994 in gate question. That's why we have used here again once again. So as the aperture width is keep on increasing in the flat top sampling, this will lead to reduction in the useful information, high frequency common information. Okay, so the corresponding option here is for this question is A. Attenuation of high frequencies in reproduction. So confirm there will be loss in the high frequency component when we try to recover original signal. So that is the drawback when we use flat top sampling with increasing pulse width. So next question, a 1 kilohertz signal is flat top sampled at the rate of 1800 samples per second, and the samples are applied to an ideal rectangular low pass filter with cutoff frequency of 1100 hertz. Then the output filter contains. Okay, there are again 4 options. Okay, so here in this question they are given FM as 1 kilohertz, FS as sampling frequency as 1.8 samples per second. Okay, so the frequency component, they ask for what are the frequency components available when used as a low pass filter. So I'm going to send this message signal to a low pass filter. Okay, so with the minimum cutoff frequency of 1100 hertz. Okay, so the sampling rate is 1800 samples per second. Okay, so now it is available sampling period. How many frequency components are available? Okay, the formula is n into fs plus fm, where n is nothing but integer, any integer. Okay, it starts from 0, 1, 2. Okay, so now we need to substitute 1 by 1 value. Okay, so first substitute n is equal to 0. If n is equal to 0, what will happen? 0 into fs, 1800 will become 0 plus or minus. Okay, what will get? 1000 hertz is the answer. 0 plus or minus fm is nothing but 1000 hertz. Okay, so next option, substitute n is equal to 1. So keep on increasing n values, then only we will get the desired frequency range here. So they are given 4 options. This one, which is correct, we need to find it. Okay, so next n is equal to 1, what will happen? 1 into 1.8. That's 1800 hertz. Okay, plus or minus 1. If you add plus 1, what will happen? You will get 2800. If you add minus 1, you will get 800 hertz. Okay, now we got 2 frequency components here when n is equal to 1. Similarly, substitute n is equal to 2. So n is equal to 2 means what will happen? 3.6 plus or minus 1. Okay, this minus 1 means what is the answer? Minus 1 means 2.6 2600 hertz, plus 1 means 4600 hertz. So if we keep on increasing, still the values keep on increasing. Okay, now for this n is equal to 0, 1, 2, we got 5 values. One is 1000 hertz, next is 800 hertz, next is 2800 hertz, then for n is equal to 2, we got 3600, 2600 and 4600. Okay, so now in the given problem, they are given the cutoff frequency. Because for any sampling, they will give a cutoff frequency below that only the components will be available. We need to consider those components only. So other than that, we need to neglect. Okay, if you compare all the values, you got 5 values. In this one, the values which are present below 1100, that is a desired answer. Okay, if we go to this one, here we have 1000, which is less than 1100 hertz. This is the desired answer. Then in this 2, we got 800 hertz. This is desired answer. This can be omitted. Okay. Similarly, for n is equal to 2. For n is equal to 2, here we have 2600. This can be omitted and this can be omitted. Okay. So because the cutoff frequency is given as 1100 hertz. So now the desired answer from these options. Sorry. So the desired answer from these options . Okay, so this is the desired answer for this one. So for the given frequency, for the given message signal, and for the given sampling frequency, we have find the other frequency components for the formula called n into fs plus fm. Then we have started substituting the n values, which is nothing from 0, 1, 2, 3. Then we have find this cutoff frequency range whatever values are available, that is the desired answer. So we have gone through it and we found that 800 hertz and 1000 hertz are the components available in the given cutoff frequency of 1000 hertz. Okay, so this is the desired answer. Next, the Nyquist sampling interval for signal sync 700T plus sync 500T. Okay, sync is nothing but sine t by t. Okay, sync function is nothing but sine pi t by pi t. It is nothing but your sync function. This will be in the format of this sync function. Okay, this is the formula. So sync and put it, so they give like sync means this is the format. Okay, so now in the question they are given, they asked to find a sampling interval. So now they are asked to find the Nyquist rate. Nyquist rate is nothing but I already said that Fs is equal to 2Fm. The minimum sampling rate is nothing but which we are calling as Nyquist rate. Okay, so now they are given this signal value. From this one we need to find the desired Nyquist rate. Okay, so now we will start. Signal is given. The signal is given. Signal sync 700T plus sync 500T. Okay, so this can be represented as I said. Sync is nothing but sine pi t by pi t. Okay, so it's nothing but sine 700 pi t by 700 pi t plus sine 500 pi t by 500 pi t. Okay, so in this one we need to consider maximum frequency component because the received signal. Okay, whenever we transmit information, we need to consider maximum frequency. Then only we can able to allow the less frequency components also in the desired signal. Okay, instead of this 2 pi FM 700 pi, if we take 500 means what will happen? We can miss this information because compared to 500, 700 is larger. That means we can't able to allow a larger value in the smaller frequency, but we can able to allow a smaller value in the larger frequency. That's why we need to consider maximum frequency component. Okay, so here 2 pi FM is nothing but the maximum frequency component is given as 2 pi FM is nothing but 700 pi. Okay, then the FM, the message is given as 350 to FM. So which is nothing but 2 into FM is nothing but we got 700 hertz. Okay, so in this option, the desired answer is Fs sampling interval is nothing but 1 by Fs. We found that C is the answer. 1 by 700 second. Okay, so always whenever they give a signal, kindly consider the maximum frequency component. Then only we can able to allow the remaining minor frequency components in the available maximum frequency component. If we consider the minimum frequency component, what will happen? We can't able to allow the maximum frequency components in the minimum frequency. So that is the main thing. So here in this two, this is the maximum frequency component. Okay, that's why I consider this one. Then from the I have solved the get the desired answer. So next, the Nyquist sampling frequency in hertz of a given signal by 6 into 10 power 4 sync square 400T into 10 power 6 sync cube 100T. Okay, so again they ask to find the Nyquist sampling frequency. So given problem 6 into 10 power 4 sync square 400T into 10 power 6 C cube 100T. So now I must split these two into two components, F1 into F1 of T as the first part, F2 of T as the second part. Okay, so which is nothing but F1 of T. F1 of T is equal to 6 into 10 power 4 6 sync square 400T, and F2 of T is equal to 10 power 6 sync cube 100T. And we know that the formula is F1 of T into F2 of T, that is time domain response is equal to frequency domain response. Okay, F1 of T, that is conversion time domain, is a product of frequency domain. Okay, so F1 conversion of F1 F2 gives a product of frequency domain. Okay, so now bandwidth of F1 of W. Okay, so now the bandwidth of F1 of W is given as 2 into 400 radians per second, because here they're given as 400. So everything is radians per second. That's why 2 into 400 radians per second. Okay, we've got 800 radians per second. Or else we want to convert this into hertz, it's nothing but by 2. Then we will quote as 400 hertz. Okay, so here they're given sin square. Okay, so they're given sin square here. That's what is 2 into 400 seconds. In this term, they're given square term here. This cube term means this into 3 times. This sin per 4 means 4 into the maximum frequency component. Okay, so here in the first f1 of t, they are given sin square. That's why 2 into 400 second, radians per second. Okay, we got 800 radians per second. Then we want to convert this into hertz, just divided by 2, we got 400 hertz. This for first f1 of t. Second is nothing but 10 power 6 sin cube 100t. So sin cube here they given. So f1 of w is nothing but 100 into 3. That's why we got 300 radians per second. Okay, so all we got as 150 hertz. Okay, so then f1 fw will have bandwidth of 150 hertz only, because since the product of 2 spectrum, if the product is 2 spectrum, this is the minimum hertz which is required. The sampling frequency is given as 2 FM. FM is 150 hertz only. That's why 2 into 150 will get 300 hertz. Okay. So now in the given options, we can find that the option is available in B as 300. Okay. So this is a 2 marks question which is asked in 1989 gate question as gate question. So next question is, 4 independent messages have bandwidths of 100 hertz, 100 hertz, 200 hertz, and 400 hertz respectively. Each is sampled as an Nyquist state. Okay, so Nyquist state is nothing but f is equal to 2 FM. Okay, and the samples are TDM, time division multiplex, and transmitter. So the transmitter rate in hertz is. Okay, so here they get 4 message signals. So everything is Nyquist stated. Nyquist state is nothing but 2 FM. 2 FM. Okay, so they given FM. So now what you do for every message signal, we need to do this one. Okay, so for first message signal, FS1 is taken as FS1. 100 into 2 will get 200 hertz. For second message signal, again 100 into 2 will get 200 hertz. And for third message signal is nothing but 200 into 2, 400 hertz. And fourth message is nothing but 400 into 2, so 800 hertz. Okay, just add all the values. We'll get, because this is time division multiplex, so we need to add all these values, then we will get the number of samples per second. Okay, so the answer is 1600, 800 plus 400 plus 200 plus 200. So total is nothing but 1600 samples in 1 second. Okay. So if we go this one, the option is A, 1600. So next question. So a signal x of t is equal to 100 cos 24 pi into 10 cube t is ideally sampled with a sampling period of 50 microseconds and then passed through an ideal low pass filter with cutoff frequency of 15 hertz. Okay, which of the following frequency so here we represent so you've got 20 kilowatts. Okay, so I'll be sampling the signal will have frequency FM and FS plus FM. So we have two components. One is FS, FM, and FS plus FM. FM is given as 12 kilohertz. Okay. The next component is FS plus or minus FM is given as 20 minus 20 is FS value, and FM value is 12 kilohertz. That's why 12 kilohertz and 20 minus 12 is 8 kilohertz. Okay. So these four options we got 12 only, 8 only. These two are not available, and 9 is not answered. The correct answer is D. 12 and 8 hertz. Okay, because we got FM as 12, and the next component is FS plus or minus FM. Okay, for FS minus FM will gives 20 minus 12, 8 kilohertz. That's why the desired answer is 12 and 8 kilohertz. So next question, let x of t is equal to 2 cos 800 pi t plus cos 1400 pi t into x of t is sampled with the rectangular pulse train shown in the figure. The only spectral components in kilohertz present in the sample signal in the frequency range 2.5 kilohertz to 3.5 kilohertz. So this is given here. The diagram is given spectral components. They are asked to find the values present in this range 2.5 kilohertz to 3.5 kilohertz. They are given t as 10 power minus 3 seconds. Okay, they need to find this in this range what are the values available. Okay, so now from the known things, given t is equal to 10 power minus 3, the frequency is nothing but 1 by 10 because t is equal to 1 by fs, or fs is equal to 1 by ts. Okay, so you will get 1 kilohertz. Okay, so now we need to determine the frequency components of this pulse train. Then we need to apply the Fourier series coefficient Cn. Okay, we need to find, if we want to determine the frequency components in pulse train, we need to find the Fourier series of the coefficient Cn. Okay, the Cn formula is given as Cn is equal to 1 by T naught. Here, the range is given here. In this range, they have to find, that's why minus T naught by 6 to T naught by 6. This is the integral limits. A into e power minus j n omega naught t dt. Okay, if we integrate this value, we'll got 1 by t naught a by minus j n omega naught e power minus j omega naught t into minus t naught 6. The limits are t naught by 6. Okay, now substitute this limits value in this thing. You will got j by t naught minus j n omega naught into e power minus j omega naught. Instead of in the place of t, substitute t naught by 6 once, then substitute minus t naught by 6. Okay, we will got t naught by 6 minus e j n omega naught t naught by 6. Okay, so this entire thing is nothing but sine function. There's 2j sine function. We use trigonometric formulas here. Okay, if you apply this one, we got Cn is equal to a into 2j t naught j n omega naught sine pi n pi by. I applied trigonometric formula here, so that's why I got. The given equation is converted into this term alone. This term alone is converted into 2j sine theta. Okay, theta by 2. So that's why we got this one. A by 2 naught 2j by j n omega naught sine n pi by 3. Okay, so this is the desired outcome. A n by into sine n pi by 3. Okay, so now we from Cn we can see that the harmonics are 1, 2, 3, 4, 5, 7. Just substitute this value here, then we will get the desired answer as 0.4 kilohertz and 0.7 kilohertz. Now again, from this, the samples will be x of t into p of t. Okay, so now substitute 1, 2, 3 values. X of t, 1 means 1 plus or minus, because here we got two components, 0.4 and 0.7. So from this one, 1 plus or minus 0.5 and 1 plus or minus 0.7 kilohertz. And second thing is 2 plus or minus 0.4 and 2 plus or minus 0.7 and 3 plus or minus 0.5 and 3 plus or minus 0.7, etc. We go on like this in the frequency range of 2.5 kilohertz to 3.5 kilohertz. Okay, so in this range, if we do all the calculation, the desired outcome is this one. Because they are given the ranges by just substitute 1, 2, 3, 4, 5, 6, 4, and substitute the values. Okay, then only two components available. That is 2 plus or minus 0.7, then 4 minus 0.7. Because this is the range which they are given. In this range, Only these two values are present. Okay, so from the given options, just check it whether we have 2.7, 3.3. We'll get one option from this. That is nothing but the option 2.7 and 3.3. Okay, so next question. The Nyquist sampling rate for signal S of t is equal to sine 500 pi t by pi t. So they are given that is sinc function, expansion of sinc function. Okay, sine 500 pi t by pi t into sine 700 pi by pi t is given by. So again they asked to find the Nyquist sampling rate. Okay, so given thing is S of t is equal to sine 500 pi t by pi t into sine 700 pi t by pi t. So again, just multiply it. We got half 2 500 pi t into sine 200 pi t by pi square by t square. Okay, so these two will get cancelled and we'll get the same equation as it is. So now we know again apply the trigonometric formulas. Okay, 2 sine A sine B formula. Okay, so to this one we got cos A minus B minus cos A plus B. Okay, so half into 700 pi t minus 500 pi t minus cos 700 pi t plus 500 pi t. So that is the outcome is 1 by 2 pi square t square into cos 200 pi t minus cos 1200 pi t. Okay, so this one the maximum frequency component is nothing but 1200 by 2 pi. Because as I said, in the given values, take the maximum frequency. Then only we can able to allow the minimum frequency in this given maximum frequency. If we take this value, we can't allow this 1200 value. Because this minimum frequency is a maximum frequency. So that's why we need to consider always maximum frequency alone. Okay. So from this one, just substitute the formula Fm is equal to maximum by 2 pi. This 2 pi to pi will cancel. The final outcome is 600 hertz. Okay, so Fm is nothing but 600 hertz. So the Nyquist straight formula is nothing but Fs is equal to 2 Fm. So Fm is 600 hertz, which we got right now. The answer is 2 into 600. The answer is 1200 hertz. So B is the option. 1200 is the answer. Okay. So next is we will go for pulse code modulation. Okay. So now, so till now everything is sampling. So PCM is nothing but the basic first stage of stage is using digital communication. Okay. A simple method how we are going to convert the given analog signal into a digital communication. Okay. So the first method is PCM. As I said, sampling, quantization, then we are going for encoding. So these are three blocks which required to convert our given analog signal into digital signal. Then we are going to pass it through a channel. From this receiving it, what we need to do, again we need to convert it back, that is D2H should be done. Digital to analog conversion should be done. Then we need to extract the signal, position signal, that is analog signal. Okay. So typically for any system, my input is always a analog signal, my output is always a analog signal. In between, the thing which is happening is nothing but digital. Okay. So this pulse code model is the basics thing. A simple methodology, first methodology for converting any given analog signal into digital signal. Okay, so based on we will see some problems. So here an analog voltage in the range 0 to 8 volts is divided by in 16 equal intervals for conversion to 4-bit digital output. Okay, so here they consider that. So this is a analog signal. So sampling and quantization is done. So each sample, okay, each sample, each amplitude is considered with 4 bits. 4 bits. Okay, so here 4 bits, here 4 bits. For each analog signal, they are converted to digital with the help of a 4-bit value. Okay, 4-bit value means what we'll get? 2 power 4 is nothing but we'll get 16 levels. From 4 zeros to 4 ones. Okay, so each value, each signal has a unique value from this 16 levels. They have to fix it because they are given 4 digital output. So each sample they are considered as a 4-bit. That's why we get 16 levels. Okay. So now, so here dynamic range or voltage is given as, so the voltage which they given as 0 to 8 volts. So here the number of levels which is given in the problem is 16. So now they ask to find the error. So they ask to find the error. Okay, so because here what we are doing is we are converting it. We are converting our given analog to digital signal. So confirm while doing conversion, there will be certain losses. The loss is nothing but showing as quantization error, because sampling is nothing but we are converting a given continuous time signal into discrete time signal. Whereas here quantization is nothing but we are converting our given continuous amplitude signal into discrete amplitude. So this process of conversion, confirm we are going to miss certain information, because pure analog to analog no issues, but while converting, confirm there will be some rounding off of some values to the nearest possible digit. So at that time we'll get some round off error or truncation error. Okay, so those errors can be considered as quantization error. Okay, so quantization error is introduced in digital communication. Okay, so that's why when we are using digital communication, we can't expect that the outcome is 100%, because this conversion process confirm there will be minimum errors introduced while converting our given analog signal into digital signal. Okay, so here quantization error is given as QE is nothing but step size by 2, where delta is the step size, is nothing but dynamic range by L. So here dynamic range is given as, that is the voltage range is given as 0 to 8 volts, is nothing but 8 volts. As 8 volts here. Then L is the level. Level is nothing but we are considering 2 power 4 bits, because each sample they are considered as 4 bits. So 4 bits is 16 levels. So L is equal to 16 levels. That's why substitute is 2 values here. So 8 by 2 power is nothing but 0.5. Okay. So Q is nothing but step size by 2. Okay. So here delta step size is nothing but 0.5, and the Q result Q is nothing but 0.5 by 2, which is nothing but 0.25 volts is the quantization error for the given problem. Okay, so this is a fill in the blanks option. There's no choices. So accordingly you write. Okay. So compression in PCM refers to compression in PCM refers to relative compression of. Okay. So in PCM, combining is making SNR uniform with respect to the signaling amplitude. Okay, combining is nothing but compressing the given signal. Okay, compressing at the transmitting end, and after transmitting it and receiving again, we need to expand it. So that the process is called combining. Okay, so combining is nothing but whatever we are doing is we can't able to send the high frequency as it is. Otherwise, we need to what we do is we need to compress at the starting end, and the receiving we need to expand it. Then only we can able to accept the original information. That process is called as combining. Okay. Here they given compressing and expanding. Okay, so the data is compressed, sent, and then expanded at the receiving end. Okay, so compression is maximum used for higher signal amplitudes, because we don't have that much frequency or that much components to send as it is. That's what we'll do. Higher amplitude signals will be compressed at the transmitting end. Then what I will do at the receiving end to extract the original information. At that time, I need to expand it to the original information. That process is called as combining. Okay, so here the option for this one is higher signal amplitudes. Okay, so digital, if we talk about digital, frequency is constant. Here the only phase and amplitudes keep on varying. Okay, since 4 options they are given: higher signal amplitudes, higher signal, lower signal amplitudes, lower signal frequencies, higher signal frequency. So frequency typically we will discuss in analog signals. Here frequency we will not discuss. Maximum, the 2 things which is varying, maximum is varying is phase and amplitude only in digital signal. That's why here combining results in higher signal amplitude. So higher signal amplitude is compressed at the starting end, that is transmitting end. Then at the receiving end, we need to expand it to get the original version of the information which I transmitted. So that process is called as combining. So next, the signal to quantization noise ratio in an n-bit PCM system. Okay, so here they given in PCM system the quantization noise error, so SNR, signal to noise ratio, is depends upon. So we have the formula called S by N formula for PCM is given as 3 into 2, 3 by 2 into 2 power n, where n is the number of bits which we have converted. Okay, so we have, as I said, here we are each sample we are going to convert this given analog signal to a digital signal with number of bits. Okay, the bits may be 1, 2, 3, 4, 5. So previous program we have taken four bits for each sample. Okay, so always my signal to noise ratio is depends upon these bits. Okay, so that's why in the final formula also for SNR of PCM, here if we go to 1, we have got n only. Then everything is nothing but values, integer values and mixed fraction value. But here, if we go to this one, n value. Okay, if we convert this into decibels, okay, if we convert this into decibels, again the formula is 1.76 plus 600. We convert this PCM into decibel values, again the formula is 1.76 plus 600. So that means n is the number of bits. Okay, so these 4 options, the answer is depends upon sampling frequency employed. So here frequency is not available. It's independent of the value of n. No, it's a dependent. Actually, SN is dependent upon n only. So second option is not correct. Increasing with increasing value of n. So this is the correct because n is in the powers, 2 powers, 2 power n. So if n is keep on increasing, SNS keep on increasing. Okay, that's why C answer is correct. D is nothing but decreasing with the increasing value of n. So this is not correct. So answer is C only. Okay, so again, based on the formula, again we have solved the formula problem. If the number of bits per sample in a PCM system is increased from n to n plus 1, okay, the improvement in signal to noise ratio will be. Okay, so the formula we have taken only n value, 1.76 plus 6n only. So now they replace n with n plus 1. Okay, so if they replace n with n plus 1, what is the improvement? Okay. So normally SNR is given as 1.76 into 6n. Now SNR2 is nothing but 1 plus 6n into 6n into n plus 1. So we got this formula. Okay. So if we compare, just substitute SNR1 minus SNR2. Then the value is 1.76 plus 6n plus 6. So 6 dB. So answer is 6 dB. So there will be 6 dB increase per sample. Okay. So this is the desired outcome. Just substitute first n, then next is substitute with the given value, substitute n into n plus 1. So we will get the desired outcome. Okay. Okay, students, I have one more class after this one. So I will stop it here. I will share these materials with the coordinator, Subbu sir. Okay, so he will post it in a group and you can go to the remaining problems. Okay, so I have one more class after this one. Okay, so I'm going to end this session right now. Okay.
Okay, sir. Thank you, sir.
Thank you. Record பண்ணது காமிச்சிருக்கீங்களா?
Okay, sir.
Thank you, friends. Thank you. I'm going to end the session.
Thank you.